Let's solve question 1 from this worksheet. It was Physics 151, Spring 2025, either worksheet 13 or worksheet 0411. So we have a solenoid, and the solenoid is a big coil of wire, and it's wound into n turns of radius a, and the length of the solenoid is L. So L is the length from one end of this coil to the other, and then A is the radius of this circle, which will be the projection of this helix onto the xy plane. So the problem states that the solenoid is placed in a uniform magnetic field, B, which is a function of time and which is directed to the right. Now, I drew my solenoid oriented vertically instead of horizontally, so I'm going to pretend that right is at the top of the board and left is at the bottom of the board. So my magnetic field, as I look at it, is directed upward rather than to the right. So we'll just have to account for that later. And we're going to assume that this external magnetic field is increasing in magnitude with time. We want to know what is the induced EMF in the solenoid. So to work that out, I'm going to call this the area. So I'm going to make a little circle which represents the circular projection of this helix into the xy plane. Notice that my drawing here on the left has the xy plane as the plane of the board, and then these two drawings on the right actually have the yz plane as the plane of the board. So I'm going to make my area vector of this loop be, here's pi a squared, because this radius of the circle is a from the problem statement. I'm going to make my area vector point out of the page. And then here, my applied magnetic field, some externally applied magnetic field. So it's not a magnetic field created by a current in this solenoid, it's a magnetic field externally applied, which then induces a current in this solenoid. So my externally applied magnetic field is also pointing out of the board. And then by making my area vector point out of the board, then the sign convention would be that EMF bigger than 0, if the EMF turns out to be bigger than 0, will be counterclockwise. So my convention, if A points out of board, then EMF bigger than 0 will be counterclockwise. So that's the right-hand rule, where if the thumb of your right hand points out of the board, then the fingers of your right hand curl in the counterclockwise direction. So the induced EMF is minus the rate of change with respect to time of the magnetic flux through this circle, which is minus d by dt of formally the integral of the magnetic field dot the area vector. But the magnetic field is uniform inside this area, so this integral can be replaced with just a multiplication. So this is minus d by dt of the magnetic field is b of t, and it's in the k hat direction. It's pointing out of the board. It's in the plus z direction. And then dot product with, here's pi a squared is the area of one loop, and I said that my loop is pointing out of the board also. Now there's one complication here, which is that this solenoid curls around n times. So the magnetic field actually passes through the loop of wire n times because it's wound around n times. So I'm going to multiply this by n. Then k hat dot k hat is just 1. So this just becomes minus d by dt of n pi a squared, and then the magnetic field, which is a function of time. The only thing here that depends on time is the magnetic field B. So this just equals minus n pi a squared d b dt. This is the induced EMF in the counterclockwise direction. So if this is positive, then the induced EMF is counterclockwise. Because we said B is increasing in magnitude, this whole expression will be negative, so the induced EMF should actually be in the clockwise direction. So since dB dt is bigger than 0, EMF counterclockwise is less than 0. That means that the induced EMF is actually in the clockwise direction. Let's just check that. Okay, so we actually have induced is actually clockwise. Let's see if that makes sense with Lenz's law. So, and this is actually my right hand. The video is mirrored, so it looks like a left hand. So what I see is that a clockwise induced EMF would create a clockwise current, which would then create an induced magnetic field. So this is the induced magnetic field, would point into the board, And that makes sense because we have a magnetic field applied from the outside which is pointing out of the board and is increasing in magnitude. To oppose that increase out of the board, I want to create a magnetic field into the board, and that is what a clockwise induced current would do. So it makes sense that the induced EMF is clockwise, as I've drawn it. The picture in the original problem doesn't really make it obvious which way the current flows, so I tried to make it obvious which way the current flows here. Let's see if that worked out in this diagram also. So in this other perspective, I said that the externally applied field is going quote-unquote from left to right, but it's, in the way I drew it, is from bottom to top. So then the induced magnetic field, in other words, the magnetic field, which is a product of the induced current in the solenoid, must oppose that because this is increasing. So if it's up and increasing, then the induced magnetic field must be down. And to produce a magnetic field which is down, we would have current into the board on the left side here of my drawing and current out of the board on the right side here of my drawing. So that makes sense. So current going like this into the board over here, out of the board over here, would create a magnetic field that points down. So again, that makes sense that the induced current goes in the sense that produces an induced magnetic field which is opposite the externally applied magnetic field. Also, if you stare at this drawing, and here's my convention where the y-axis is to the right, the x-axis is out of the board, and the z-axis is up. You can see the way I drew this induced current. It is in the plus x direction, then it's in the minus y direction, then it's in the minus x direction. So this would be in the plus x direction, then the minus y direction, then the minus x direction if it's going around clockwise. So I think you can see that this drawing on the right is consistent with this drawing on the left if you really think hard in 3 dimensions. So part B asks us what is the direction of the induced magnetic field, the magnetic field created by the current that flows in the solenoid. So the original problem says that the external magnetic field is to the right and is increasing, so therefore the magnetic field created by the solenoid itself must be to the left. So the way I drew it, the externally applied magnetic field points up. So then the magnetic field induced by the current induced in the solenoid because of the EMF induced in the solenoid coil must point down to oppose that. So since the applied magnetic field is increasing and points to the right in the original problem or up in my drawing, the EMF induced in the solenoid will, assuming that there's some finite electrical resistance and that there's a closed circuit so current can actually flow, it will create an induced magnetic field which is opposite the applied magnetic field. So in my drawing, that means the induced magnetic field is down. In the original problem, it's to the left, opposing the applied magnetic field. So that's Lenz's law, saying that the result of an induced EMF is to oppose the change in magnetic flux. Okay, next, the external magnetic field from the first part of the problem is turned off. So there is no longer any externally applied magnetic field. Now the solenoid is connected to a power supply which applies a current I through the solenoid. We want to work out what is the magnetic field of the solenoid. So the applied current that our power supply is running through the solenoid creates a time-dependent magnetic field produced by the solenoid itself. So then that is a time-dependent magnetic flux passing through the solenoid coil. So then that induces an EMF in the solenoid itself. So that will be a self-inductance effect. So there is some EMF induced in the solenoid as a result of the magnetic field produced by the solenoid itself when that magnetic field has a time dependence because the current producing the magnetic field is time dependent. So let's work that out. So if the applied current goes into the page over here on the left side of my slice through the solenoid and out of the page over here, that will create around each tiny little wire of the solenoid. Let's see, so on the side where it's into, the magnetic field lines will circle around like that. Okay, now we want the induced EMF. So the EMF induced is minus the rate of change of magnetic flux, which is minus the rate of change of the integral of the magnetic field dot the area vector. And then we have to account for the fact that in this solenoid, which is wound n times, the magnetic field lines will actually pass through this area n times. So my magnetic field here is in the minus z direction. So in this diagram, that means my magnetic field is into the plane of the board. And I am once again going to define my area vector to be out of the board. So my area vector points out of the board. My magnetic field is into the board. And then we have to account for the fact that the magnetic field lines actually pass through this area pi a squared n times because the coil is looped around n times. So this is minus d by dt of the magnetic field. Well, this is my expression for the magnetic field. I'll just leave it as B for now. So here's b times minus k hat, because it's in the minus z direction. And then there's going to be a dot product with pi a squared k hat is my area vector. By defining the area vector out of the board, then if I get an induced EMF which is bigger than 0, it's going to mean counterclockwise. And if I get an induced EMF which is smaller than 0, it will mean clockwise. And then I have to multiply by n because I actually pass through n coils of the loop. Minus k hat dot k hat is just minus 1. I might as well cancel that minus 1 with the minus sign on the outside here. So this equals d by dt of n pi a squared b. I can plug in my expression for b, so this is d by dt of n pi a squared times mu naught n I over L, and the only thing that's time dependent here is the current I. So this EMF counterclockwise induced is pi a squared over little l mu naught n squared di by dt. This was actually two separate parts of the problem in the worksheet. One was what's the induced EMF per loop? So then there would be only one factor of n here instead of a second, because we wouldn't have multiplied by this factor of n yet. And then when you say what's the induced EMF in the entire solenoid coil, then we have this factor of n. So then this becomes n squared as I've written it here. So it appears that this induced EMF is in fact counterclockwise. And I think that even makes sense because the applied current from the outside world was clockwise. And Lenz's law tells us that the effect of induced EMF because of changing magnetic flux should be to oppose the original cause. So an induced EMF counterclockwise makes sense because that would oppose the clockwise applied current. The next part of this problem wants us to then write this in terms of inductance. So we know that the magnitude of induced EMF is this factor L that we call inductance times the rate of change of current. We often write a minus sign here to indicate that the induced EMF is opposing this change in current. I won't write the minus sign here. We'll work out the sign from understanding that the effect should oppose the cause. So in this case, we can see that this factor in front of di by dt must be the inductance of this solenoid. So the inductance of this solenoid is L equals mu naught number of loops squared times the area of each loop and then divided by the length of the solenoid. The minus sign that would be conventional here is telling us that if di by dt is in the clockwise sense, then the induced EMF should be in the counterclockwise sense. Let's check that. So you can see that the applied current is clockwise, and then if di by dt is positive, that would mean that the applied current is increasing in a clockwise sense. And you can see that the resulting induced EMF is counterclockwise if di by dt is positive. So that's why conventionally you would put the minus sign. I didn't put the minus sign here because I wrote my induced EMF in a counterclockwise sense. But you can see that the induced EMF in the clockwise sense is minus L times the rate of change of current in the clockwise sense. So if you write induced EMF clockwise in di by dt clockwise, then you need the minus sign. In this case, I wrote my induced EMF counterclockwise, and I wrote my di by dt clockwise, so I didn't need the minus sign. So we worked out the inductance of our solenoid. Now you see why the circuit symbol for an inductor looks like a solenoid. A solenoid is an example of an inductor. It has an inductance, which we can calculate. Now let's make a circuit out of our solenoid. So here's our inductor, inductance L, which is basically just a solenoid we've been using. And then we have a resistor in series with that. And then there's a switch which is currently open, and then there's a battery over here. And if the switch is open, there can be no current. But then once we close the switch, we're going to have a current I that flows this way out of the positive terminal of the battery. But the inductor is going to try to oppose the change in that current. Now the first question is, what is the current flowing through this circuit the instant immediately after we close the switch? So we know that before we close the switch, the current must have been 0 because no current can flow through an open switch. Then we close the switch at t equals 0. Now there's a trick with these inductor problems. You might remember with our RC circuit problems, as long as there was a resistor that limited the rate at which charge could move around, the instant after we changed the orientation of a switch, the charge on each capacitor was the same as the instant before we changed the orientation of the switch. And again, that was because there's some time constant. In the RC circuit, the time constant was some resistance times some capacitance, over which charge could move onto or off of a capacitor, we're going to see that in these LR circuits, there's a time constant L over R, which determines how long it takes for the current to change appreciably. So this current cannot change by a finite amount in an infinitesimal amount of time. So if the current was 0 an instant before we close the switch, then this current must still be 0 an instant after we close the switch. So the current is 0 at t equals 0 plus, the instant immediately after we close the switch. After a very long time, so we know there's going to be some time constant, L over R, over which, and we'll prove that in a moment, over which the current changes. There's an EMF induced in the inductor that tends to oppose what the battery is doing. And that's proportional to the rate of change of this current. So after a very long time, this current becomes constant. And if the current is constant, then the rate of change of that current is 0. So then the induced EMF becomes 0. So then after a very long time, the inductor just looks like a wire. So we can write the loop rule, the battery EMF. We're going to go from the battery. Our loop is going to start here at the plus terminal of the battery and go around clockwise back to the minus terminal of the battery. So we have the battery EMF minus IR minus L di by dt equals 0. That's the correct sign convention if the current that you draw is in the same direction as your loop direction. So this L di by dt term follows the same sign convention as the IR term for the resistor. So for the resistor, we know if the current is from left to right, then the left side of the resistor is at higher potential than the right side of the resistor. And for the inductor, if the current is going clockwise, so it's downward on this side of the schematic diagram, then a positive di by dt would result in the top side of the inductor being at a higher potential than the bottom side of the inductor, which has the desired effect of opposing the change in current. You can see that it's opposing what the battery is doing. So this sign convention for L di dt works. So it's minus L di dt if your current direction is the same as your loop direction. So this sign convention for the resistor IR term is the same as the sign convention for the inductor L di by dt term. So this is always true. So at t equals 0 plus, we have I equals 0. That gave us that the battery EMF minus L di dt equals 0. So the induced EMF in the inductor is just the same magnitude as the battery EMF immediately after we closed the switch. At t goes to infinity, we have di by dt goes to 0. So then we have the battery EMF minus IR equals 0. So that gives us I is just the battery EMF divided by the resistance after a very long time. Then we could ask, what happens at intermediate times? So we won't ask you to do this on an exam, but I think it's good to see how it's done in a lecture. So let's take this differential equation for I, and let's make a substitution. Let U equal the battery EMF minus IR. Then we have du equals minus R di. So the battery EMF is a constant. So then that gives us di is minus 1 over R du. And we also have then that I equals the battery EMF minus U divided by R. So then this differential equation is saying that U plus L over R du by dt equals 0. Then we can separate the variables. So this is U equals minus L over R du by dt. So du over U equals minus R over L dt. Then we can integrate both sides, and we get the logarithm of U evaluated from t equals 0 to t is minus R over L, and then we can just evaluate t from 0 to t. So this gives me that the logarithm of U divided by U initial is minus R over L times t. Then we can take the exponential of both sides here, and we get U over U0 equals e to the minus R RT over L. So U equals U initial e to the minus RT over L. And then we can go back in terms of I. So the battery EMF minus IR equals the battery EMF minus I initial R e to the minus RT over L. The current at time 0 is 0 in this case. So that gives us IR is the battery EMF 1 minus e to the minus RT over L. I had to multiply everything by a minus sign, and then I moved the battery EMF to the other side. So then the current as a function of time is the battery EMF over the resistance times 1 minus e to the minus RT over L. So we have a time constant L over R. So it's e to the minus t over time constant, where the time constant equals L over R. That was actually just given to you in this problem. I thought, well, since we have time here asynchronously, I'll derive it. Now let's use that to solve the question on the worksheet. So we can see from this expression that if t equals 0, we get I equals the battery EMF over R, 1 minus e to the minus 0, which is 0. That's good. We kind of assumed that in our solution, actually, by canceling out the current at time 0. And then, as t goes to infinity, we have the current is the battery EMF over the resistance, 1 minus e to the minus infinity. So e to the minus infinity is 0. So this just equals the battery EMF over the resistance. So that makes sense. That's what we reasoned before, kind of by waving our hands. And now we can work out the induced EMF in the inductor versus time. So the induced EMF is L di dt. So that equals L times d by dt of the battery EMF over R, 1 minus e to the minus RT over L. Okay, so this 1 does not vary with time, it's a constant. So we have, and we can pull these constants out. We have L times the battery EMF over R. This is the induced EMF, and then times the time derivative of minus e to the minus RT over L. This equals L battery EMF over R. This is this constant. The constant is minus R over L, so that minus sign cancels that minus sign. So we have R over L e to the minus RT over L. The R cancels, the L cancels, and we get the induced EMF equals the battery EMF times e to the minus RT over L. So this is the magnitude of the induced EMF, the battery EMF times e to the minus RT over L. Let's think about the sign of the induced EMF. So the current versus time has this shape that's familiar from a charging up capacitor. So the slope is maximum at time 0, and then the current reaches some asymptotic constant value at a long time after several times L over R. The induced EMF is at its maximum magnitude when the current has its maximum slope, and then it decreases exponentially, so it looks like a discharging capacitor, or it also looks like the current versus time in an RC circuit problem. So the current here is increasing. So if the current is increasing in a clockwise sense, then the inductor is trying to oppose that increase in current. And if this side of the inductor develops a potential that's higher than this side of the inductor, that indeed opposes what the battery is doing. It opposes that clockwise flow of current. So that even makes sense. So the plus sign up here and the minus sign down here makes sense for the induced EMF. And that induced EMF is as big, it's the same size as the battery voltage initially, and then it's decreasing exponentially, and then after a long time that induced EMF reaches a magnitude of 0. But it makes sense that this terminal of the inductor is at a higher potential than this terminal of the inductor because it's trying to produce a counterclockwise current to oppose this clockwise increase in current. And that's true because this current is always increasing. And then eventually that rate of increase becomes 0, so the induced EMF becomes 0.